Thank you very much for the invitation to speak here. So just to give you a little bit of background, I'm a theoretical computer scientist, and what I work on most of the time is algorithms for unsupervised learning. So most of my work has been on stuff like clustering, active learning, nearest neighbor, interpretable ML. But in the last few years, I've become interested in formalizing notions of neural machines. And so I'll be talking a little bit about that line of work today. So what I mean by a neural machine is just a machine, biological or human-made, that is capable of lifelong learning, okay? And so this is just some device that at each point in time receives some input, has to immediately produce some action or output in constant time, let's say, and has access to some memory that it can update as needed, okay? So the main thing is that in contrast to a Turing machine, which is geared towards a single computation, this machine has to endure, okay? It has to learn from experience, adapt to changing environments, and so on. So this is sort of a vague and broad notion, but there are several parts to it. Studying biological organisms in a mechanistic and algorithmic way, tying in relevant formal machine models like finite automata, recurrent nets, looking at algorithmic tasks that seem intrinsic to lifelong learning, like clustering and density estimation, and then also bringing in minimalistic computational paradigms like the streaming model or online computation. Okay, so today I'll be talking about two lines of work. One of them is about algorithms from the fruit fly, and the second is using hyperdimensional computing for building embedded devices. And you know, they seem somewhat different, but mathematically there's a great deal of commonality. And the common theme will actually be all about high-dimensional sparse representations. Okay. So let me start with the first one. So the idea here is to study neural circuitry of the fruit fly from an algorithmic viewpoint. So what exactly are these circuits doing? What algorithms are they performing? What tasks are these for? Are these tasks that we are interested in doing in computer science as well? And if so, can these algorithms be brought in to the computer context? Okay, so this work started about 8 years ago when these two people called me from out of the blue. Saket Navlakha is a brilliant computational biologist who was at the Salk Institute at that time and is now at Cold Spring Harbor and Genelia Farms. And Chuck Stevens recently passed away. He was, you know, a much loved and very eminent theoretical neuroscientist. So these guys called me up and said that we're looking at the fly brain and we're finding random projections. Can you help us analyze what these things are doing? And I myself know precious little about neuroscience, so I was very intrigued, like, well, what do you mean? Like, how can there possibly be random projections in a brain? And, but we looked, and there did seem to be random projections, and then we started peeling back further layers of the circuitry and found algorithms for all sorts of tasks, like novelty detection, approximate counting, continual learning, and so on, okay? And in each case, we were able to bring these algorithms back into computer science and found that they worked pretty well, okay? So, so I'll talk about some of this. In retrospect, I suppose it's not at all surprising that the fly has good algorithms for things like similarity search and novelty detection. I mean, these are things that Google uses, you know, in order to make money, but a fly needs it to survive. And you know, but the thing that surprised me actually is that the algorithms are, of course, to some extent, fine-tuned towards the specifics of the data distribution that the fly encounters, but not overly so. They're actually fairly general purpose. And so it was, and work well for many types of data. Okay? Okay. So what is this business about random projections in the fly brain? And by the way, feel free to stop me at any time, okay? Just at a very high level, will not go into any details here. The sort of olfactory input to the fly can be thought of as roughly a 50-dimensional input. And the first thing that happens is that it gets expanded to about 2,000 dimensions. And let me talk about how this happens because it's kind of interesting. Okay, so the fly has a whole bunch of olfactory receptor neurons, thousands of them, maybe 2,000, 3,000, but they're just of 50 types. And so the input can be thought of as 50-dimensional. And at the glomeruli, you can read off this input. Okay, so it's a 50-dimensional input about the current odor, about the current combination of odors. And what happens immediately is that these 50 dimensions get mapped up to 2,000 dimensions. Okay, so it's an expansive map. And the way this happens is that there are these 2,000 Kenyan cells in the next level, and each of them is connected to a few of the glomeruli, maybe 6 or 10 of them, okay, seemingly chosen at random. Okay, so a random pattern of connectivity. And they add up those inputs to a first approximation, okay? And so what this map is actually an expansive linear map, okay? It's taking this 50-dimensional input and multiplying it by this matrix, which is 2,000 by 50, okay? And since it's just adding stuff up, the entries in the matrix are just zeros and ones. And if each of these guys is connected to roughly 6 of these, then each row of the matrix has got about 6 ones in it. So it's a sparse binary matrix to a first approximation, okay, to a very coarse approximation. So the next thing that happens is that this 2,000 dimensional vector, which is actually very dense, okay, so because you've taken 50 dimensions and multiplied it by this matrix, is then sparsified by just retaining roughly the top 5% of the values in it. Okay, so from 2,000 you go down to about 100 entries. And since it's low precision, to a first approximation, we can just say that all we remember are the positions of the top entries. Okay, so we have this 2,000 dimensional vector, and we just remember the positions of the largest numbers. So you get this 0, 1 vector, a binary vector, which just now encodes the positions of the largest values. And now this is the tag, or this is the high-dimensional representation in which subsequent processing occurs. Okay, similarity, search, learning, whatever. So some interesting questions are, how should we mathematically model this whole process, including this, this map over here, this expansive map? And, a not entirely accurate but very simple model is just to say that this is multiplication by a random matrix. Okay, so it's a matrix that's random, chosen at random, but then fixed once and for all, and applied to all inputs. Okay, so it's a binary matrix, 2,000 by 50. Okay, each row has got 6 to 10 ones in it. The matrix is chosen at random, and then that's what's used over here. Okay, and then we'll talk about this process. Now, this is not exactly a random projection because it's increasing the dimension, but still, this sort of random linear transformation is heavily used in computer science. We understand it very well, okay? Easy to analyze. What's a little bit more interesting or from an analytical point of view is the second process, where you have a vector and you just keep the positions of the largest entries. So this is a less common operation. It's a very natural operation, but it's not something that's a common algorithmic primitive that much, okay? And so we spent a little bit of time kind of analyzing the effect of that in order to understand what the geometry is of this space over here relative to the original input. Okay, so what is the geometry of this high-dimensional tag space compared to the original inputs. And the purpose of that was to basically understand what is beneficial about this kind of representation. So this is just some of the statistics of the random mapping. Let me just skip over this. So here's the process then. You have a relatively dense input. Let's say it's d-dimensional, okay? And then you use a random linear map to send it to much higher dimension, okay? And so what is this map? It's given by an m by d random binary matrix, okay? With a certain number of ones per row, say 6 ones per row, okay? And then we have, so that's this intermediate value y, which is much higher dimensional. And then we retain the positions of just the largest entries of y. And that's this final tag over here, which is the vector z, okay? And so the question is, how does this relate to this, okay? So what turns out to be the case is that if you look at two inputs over here, okay, so if you look at two different x's, x and x prime, and you look at the high dimensional representations that they produce, z and z prime, then the dot products between the z's are the dot products between the x's raised to the power of c. And then there's some constants over here. Okay, and in this case, c is whatever it is, 6 or 10, something like that. So what that means is that if these two vectors, if the two inputs were actually very close together, where their dot product was close to 1, then their tags are also fairly close together. Whereas if the original inputs were just a little bit far apart, then their tags are almost orthogonal, okay? Get mapped very, very far. So in other words, distances get blown up in this nonlinear way. Okay, so stuff that's close together, very close together, remains fairly close together, and stuff that's a little bit far apart gets mapped very, very far apart. Okay, and so this is the effect of. Oops. Okay. Okay, great. Now this is in the case where the x's are Boolean. Okay. And we looked at several cases, Boolean, real valued, and so on. And they each give similar results, but we don't actually have a unifying result of this type. Okay, so this is in the Boolean case, but I think it's representative. So it's a nonlinear blow up of the distances. So what's so good about this? So first of all, it is a locality sensitive map. So if the x's are very close together, the tags remain fairly close together, okay? And so experiments on nearest neighbor search with this work out very well. And that's what we originally did. But then we started looking at further layers in the circuitry, and we found that this representation facilitates all sorts of further computations, in particular classifier learning. So we found this novelty detector in the next layer, an approximate counting mechanism. These are essentially all different types of classifiers. And so why does it facilitate classification? So that's something that I'll talk a little bit more about soon, okay? And it's also not hard to see that this representation has the kind of universal approximation property that we're familiar with from neural nets. So as neural nets, it's known that if you take any continuous function, you can approximate it using a neural net as long as there are enough hidden units in the neural net. And something very similar holds over here. If you take any continuous function of your input, then that function is almost linear in the representation. So even though the original function was nonlinear, in terms of this new high-dimensional representation z, the function is almost linear as long as the dimension of z is large enough. Okay? And what's interesting here is that this holds even if the level of sparsity in this representation is the same. Okay, so you can fix a level of sparsity, like only 100 non-zero entries, and that's enough. Okay. Okay. So now I'll talk a little bit about one of the benefits of this representation, and just in terms of some work that we did about classifier learning without catastrophic forgetting. Okay, so a sort of fly-inspired classification problem. So catastrophic forgetting is something that is commonly described as a problem with neural nets, where if you train them on several tasks, when you get to the latest task, it forgets some of the earlier ones, okay? And one of the early examples of this was this experiment of McCloskey and Cohen, where they were training a neural net to do single-digit arithmetic. Okay, so they trained a neural net that looked like this. This is the first digit, this is the second digit, and then this is the operation, which in their case was either addition or multiplication. Okay? And so you put the inputs over here, then you had some hidden units, and then the outputs are 2 digits in general. So they trained the neural net to do this, and in this case, there just aren't a lot of combinations, because it's just single-digit additions and multiplications. The total the total number of combinations is something like 100 or 200, and it was very easy to train the neural net to do this. But then they tried to do it a different way. They said, well, when we're teaching a child how to do this, we start with the easy one, so let's try doing something like that. So they said, first let's do addition by 1. So one of the numbers was always 1. Then they said, okay, now that we've learned how to do addition by 1, let's do addition by 2. And so then one of the numbers was always 2. And then let's do addition by 3. And then they found that when they were trying to do addition by 2, it forgot how to do addition by 1. And then when they're doing addition by 3, it forgot how to do addition by 2, and so on. And so that was catastrophic forgetting. Okay? So I think it's pretty obvious that this would happen, but this is considered, it's pretty clear that something like this would happen, but still, this was given this name and considered a problem. Okay. So, in a recent paper, we looked at the old perceptron algorithm, and the first thing that we wanted to point out is that, this catastrophic forgetting is not a neural net specific thing. It would hold even for something really simple, like the perceptron algorithm for linear classification. And then we noted that the perceptron itself is not something that's especially easy to implement in a fly brain, okay? And we looked at a more natural version of it and found that, in fact, it would not suffer from catastrophic forgetting, okay? And so let's just look a little bit at that. Okay, and feel free to ask questions at any point. So let me just remind you of the perceptron algorithm, okay? So this is a super simple algorithm, just 5 or 6 lines of code. And it's an algorithm for linear classification, okay? So let's say you have data in d-dimensional space, and let's say that you have k classes, 1 through k, okay? So what this algorithm does is that it maintains a linear function for each class. So for class J, your linear function is wj.x plus bj, okay? So for class 1, it's w1.x plus b1, class 2, w2.x plus b2, and so on. So you have a linear function for each class, and now when you want to predict on a new point, every class evaluates their linear function, and the biggest value wins. Okay, so that's how you make a prediction. So that's the perceptron model, okay? So you have these k different linear functions. And now how do you learn one of these things? Well, you start by initializing all the linear functions to 0. And then you start going through data. And at each moment in time, you get some data point, okay? Some point and its label. So you get a point, you make a prediction. You see which of your linear functions is biggest. And if your prediction is correct, then you don't do anything, okay? because everything's fine. If the prediction is wrong, then you have to update your model. Now, there are k different models because you have k classes. So which ones do you update? Well, you update two of them. The model for the correct class and the model for the class that you predicted, but which was not correct. So for the correct class, you update the model to move it in the direction of the data point. And for the class that you predicted, which was not correct, you update the model to move away from the data point. Okay? And so that's it. And you keep doing this. And the amazing thing about this algorithm is that no matter what the sequence of data points is, as long as it's actually linearly separable, as long as there is actually a set of linear functions that will correctly classify them, this will converge after finitely many mistakes. Okay? And so this is sort of the classic perceptron algorithm. Okay? So this is just for linearly separable data. It's just learning linear functions. And so the first thing we did is to point out that this also catastrophically forgets. Okay? It's easy to construct a data set where you first learn W1 really well, and then you try to move on to W2, but you mess up W1, and then you try to learn W3, and then you mess up the other ones. So this problem occurs equally for this algorithm. Okay? It's not anything having to do with the complexity of neural nets or anything like that. It's simply the fact that over here, when in addition to moving the correct labels predictor, you're messing around with the predicted label as well. Okay, and that's really the problem. Okay, and so I won't go through that example. And then we said, well, let's just look at a much simpler variant of this algorithm, and one that would be much easier to implement biologically, okay? So here what you do is when you get a data point, you don't change the wrong label, okay? You just change the model for the correct label, and you just add the data point to that vector. Okay, so that's it. So it's a much simpler algorithm, okay? And over here, I've gone from x to phi of x to allow an alternative representation, okay? So it's a simpler algorithm. We just have been calling it the associative perceptron. And likewise, you can introduce constants over here, okay? So it's not hard to see that all this does is to move the weight vector for each class towards some multiple of the mean for that class. That's all it's doing, okay? So it moves the weight vector to some multiple of the mean. And by messing around with the alphas and betas, you can, for example, make it just do the recent mean rather than the mean over all time. You can do stuff like that, okay? Okay, that's fine. So for each class, we're just getting the mean of that class, roughly. That doesn't sound like it's powerful enough to solve an arbitrary, linearly separable problem. And that's true, okay? So what kind of problem can this solve? Okay, so the sort of problems it can solve is something that has this characteristic, okay? So here's what you need for this algorithm to work. So it's not as powerful as general linear separability, but it solves any problem that has the following characteristic. For most points, the average dot product with other points in the same class is greater than the average dot product with points in other classes. That's it, and that's all you need, okay? So you just need it to be the case that for most points, the average dot product with the same label points is more than the average dot product with another label's points. And if that holds, then it's easy to show that the whole thing works very well, okay? But when would this hold? So it seems like a natural property. And one of the things we do in this paper is to show many examples of when this does not hold for the original data, but the high-dimensional sparse representation creates this kind of separation. okay? For the simple, for exactly, you know, for the reason that it blows up these dot products in that sort of nonlinear way. Okay? So somehow the representation enables an easier algorithm that does not suffer from catastrophic forgetting and so on. Okay. So there's one. So I just wanted to put out one open question that if anybody's interested in, I'd be very happy to talk about. So over here, this representation where you start from a lower dimensional input and go to this very high dimensional sparse representation, I just sort of think we were just sort of treating this as a fixed representation. It's random, but you choose the random matrix in the beginning, and then it's fixed, okay? However, there is potential to actually learn or to adjust this representation over time, perhaps in response to a changing distribution of inputs. So I think one interesting question there is that it's easy to think of nice ways to adjust the representation. But what happens to stuff that you learned in the old representation? And I think that would be kind of an interesting thing to analyze. Okay, so as you change the representation, what happens to stuff that you learned using the old representation? How do you hold on to it? And what are nice models of that? Okay. Okay, so the last thing I wanted to talk about is something rather different, at least on the surface, and that is about this notion of hyperdimensional computing for building embedded devices, okay? And this is, so this actually is a trend in computer architecture, which I know absolutely nothing about, okay? But so I think that the dominant thing that we always hear about architecture is that, essentially they're grappling with the huge compute needs of AI, okay? But in addition, I think there's another trend, which is a desire to push a lot of computation into very low power, simple devices, okay? Into low power embedded, is to push more computation into these kinds of devices. And it turns out that in this world, there has been a renewed interest in some of the vector space architecture models from the 90s. For example, Canerva's model of hyperdimensional computing, okay? So the way this started up is that these two people called me up from out of the blue. Tayana Rosing is a professor at UCSD who builds these embedded devices. And Anthony Thomas was a graduate student who ended up being co-advised by us. And so they called me up and they said that we're building these embedded devices, and they're full of random projections. So can you help us analyze them? So I was very intrigued, not knowing anything about architecture. And so I found out a little bit about hyperdimensional computing, and we started working on this. And again, in terms of mathematical analysis of these kinds of systems. So what is this hyperdimensional computing? So hyperdimensional computing is a little bit of a pretentious term, but it describes a very, very simple model of computation, okay? So here's what it is. It's basically just two principles. First of all data gets mapped into some super high dimensional space, okay? So let's say the data originally lies in a space X. The first thing you do as soon as you get any data is send it to this very high dimensional space that we'll just call H for high dimensional, okay? Or hyperdimensional. And how do you map it? Using some sort of encoding function phi, okay? So everything gets sent to this super high dimensional space. And then in that high dimensional space, you're only allowed to do super easy stuff. Either element-wise addition, which is called bundling, or element-wise multiplication, which is called binding, or scalar multiplication. That's it, okay? So those are the only operations you're allowed in this very high dimensional space. And these are things that you can do easily using low precision, low power kind of hardware. And that's kind of the appeal, okay? So you do these kind of simple operations in the very high dimensional space, and then to read out the answer, it's typically done using some kind of dot product. Okay, so that is the hyperdimensional computing model. Okay. So let me just give you a couple of examples of how this works. So for instance, let's say that we want to store a set of items. Okay, so we have some set of items in the original input space. Let's say the set is x1 through xm. All data has to be transformed into this high dimensional space, so we encode all items. This is the high dimensional version of the items. And then we just add them up, okay? So each of the x's gets transformed into the high dimensional space. We have m of them, we just add up those vectors, okay? And so the set is stored as a single high dimensional vector. Now how do we check if something is in the set? To check if a certain element x is in the set, we look at its high dimensional version and we take the dot product with this stored entry. And if it's greater than some constant, we say yes, it's there.
And throughout your presentation, I've been waiting for a connection to be made, and maybe you're coming up to it. With all the work on kernel machines, support vector machines, all these things from back in the 90s and early aughts, whatever they're called, where you blow things up into a very high dimensional space. Because, for example, a support vector machine, it's all linearly separable in a very high dimensional space. There's a very, very well-developed theory for it, very sophisticated. And there's also things like overcomplete dictionaries and stuff like that. Should I be thinking of that, or am I misconceiving of where you want to see this lie with respect to this other kind of work?
No, I think that, yes, indeed, this, you can think of this using a lot of the language of kernel machines. Okay, so in kernel machines, essentially what happens is that a simple dot product in the original space is replaced by some other kind of similarity function, and that similarity function corresponds to a dot product in some much higher dimensional space. Okay, possibly infinite dimensional. And in fact, it can also be realized using randomized maps. Okay, so it's possible. So once you specify a similarity function, you can realize that function using some sort of randomized maps. Right, so at that level, there is a lot of similarity, but what's happening here is that the starting point is really a certain more limited family of randomized mappings into higher dimensional space. And so it's not the kernel function that we start with, but it's a certain sort of high dimensional expansive map. And the question is, what similarity function does this produce? And what are the benefits of it?
So you're sort of going after things the other way around. Here is a way of doing something like a kernel that's a particularly simple kind of a kernel. It's what are the properties, as opposed to saying, by decision theoretic criteria, what's the best kernel?
I would say that that's, yeah, I would say that that's right. You start with a very simple expansive map, and you say, what kind of similarity function am I getting out of this? Rather than, oh, I would like to have a Gaussian similarity function. What kind of map would give me that? Yeah.
Speaking of connection to other approaches, in the earlier part of your talk, you were talking about industrial forgetting. Both of naturalistic and sort of steps continual to overcome that industrial forgetting and your solution. Those ones that you comparison quantitatively.
Yeah, well, yeah, I didn't say anything about that, and nor was I planning to. But since you asked, let me say a little bit about it. Yeah, so so our solution was simply to not have catastrophic forgetting at all, so that there was nothing to correct, okay? And that's what happened with the associative perceptron. But I think that, yes, randomized replay would be a really, it's something that is kind of a nice intuitive idea. I think it is somewhat lacking in analysis, but one very nice setting in which to analyze it would actually be the perceptron algorithm, since that's something that we can analyze pretty well. And so that would be a really nice setting in which to do it. But I didn't bring it up simply because this associative variant of the perceptron does not actually suffer at all from catastrophic forgetting. For this, yeah, I mean, it's just a very simple idea, which is when you make a mistake, don't mess with other classes. And it's very, it's easy to do that when each class has its own linear function. It's not, it's not a complicated thing to do. Okay, so let me do, yeah.
Did you say catastrophic forgetting gets resolved if you change the algorithm like you were explaining?
Yes, that's right. This is just an algorithm that doesn't suffer from that problem. So, I mean, so the starting point was to say that, yes, neural nets do suffer from this. And in fact, so does the perceptron. But here's another way to do the perceptron where there's no catastrophic forgetting at all.
Does it give you excellent results like neural nets do?
Well, neural nets give you arbitrary nonlinear boundaries, okay? The perceptron does linear classification, but if you precede it by a large enough expansive map, then once again you get arbitrary continuous boundaries, okay? But yeah, any other questions? Yeah.
So kind of piggybacking on that question, if I take like a modern neural net and kind of take your thing and like insert it in between every single part, would I suddenly make it not catastrophically forget?
Well, it's something that you could do at the end, and so we have a bunch of experiments of this type. Yes, it's something that you could do just at the top layer. So the top layer in a neural net is typically a logistic regression. And you could do something like that at the very top, yeah. Okay. So I was going to give you a few examples of this kind of hyperdimensional computing paradigm, okay? Like, how do these hyperdimensional computers work? So this is how you would store a set, okay, as a single vector. So you can store an arbitrary collection of items as a single vector. Here's how you would do a simple classifier, okay? And so these are commonly implemented now on these devices. So let's say that you have K classes, and you have a few examples of each. How do you store this? Well, you create a vector for each class. And the vector is just the sum of the encodings of all items in that class, the average, okay? So it's just the average of each class, a lot like the associative perceptron. And to classify a new point, you just take the dot products of each of these class vectors with the encoding of the new point and return the largest one. Okay, yeah.
Just so maybe I'm understanding it correctly, is the intuition, for instance, for the set membership, that because we've expanded to such a high dimensional space, that in all likelihood, if we just took a random vector, the dot product would be 0, because like most of the entries won't be shared?
Okay, good, yeah. So the question is, like, why would this even work? Okay, so we're trying to store these M items. We look at a high dimensional encoding of each item, and we just add them up. Okay, why would this work? What property do we need for this encoding in order for this to work? And indeed, an arbitrary encoding would not be good. What you need is for distinct items to map to orthogonal vectors, or to vectors that are almost orthogonal. And as long as you have that, everything's just fine. Okay, and so we'll talk about that a little bit more. And similarly, over here, this is a very simplistic classification scheme. And the question is, what properties do you need for this encoding, for this classification scheme to actually work? Okay, so that's kind of the main question in this area. So what's happening is that these devices are being built. Some sort of, encodings are heuristically chosen. These sort of classifiers and data processing operations are defined like this. And it's not entirely clear whether they are guaranteed to give you good answers or not. And so what we were interested in understanding is what are the kinds of encodings under which these simplistic sort of methods actually provably give you the right answer. Okay. And so I'll say a little bit about that. So that's what we were looking at. Okay. So in other words, what sort of encoding should be used in these vector space architectures? So the first thing we looked at was discrete data, which is, for example, people's names, movies, books, the sort of things that you would build a set out of. And so what I said before was that for data like this, all you need is that the encodings of distinct items are almost orthogonal to each other. And this is a very standard notion in linear algebra. We usually just say that the encodings are incoherent, okay? And so the dot product between any two, this should actually be a max, sorry, between any two distinct items is at most some small number, like 0.1 or something, okay? Close to 0. And you can also show that if you just pick these encoding vectors at random from +1, -1, you achieve this, okay? And so that validates what is currently done in practice, where these encodings are just picked at random. You just pick a high-dimensional vector +1, -1 at random. And indeed, it'll have this property, and so therefore, these operations will work. So recently, it's been shown by Ken Clarkson and others that, in fact, this hyperdimensional computing on discrete data is actually very closely related to the algorithmic paradigm of linear sketching. And so they have formalized this connection and made it very nice, okay? And so this is an area that's been studied a lot in algorithms over the past 2 decades. It's a kind of algorithm for large data sets, whereas each data item comes in, you take a linear projection of it and add it to some sketch that you already have. And it turns out that this is very closely related to hyperdimensional computing on discrete data. Now, for continuous data, the kind of embedding that's used is a little bit different. You typically take the data point and multiply it by a matrix, by a random matrix that makes it much higher dimensional. And then you threshold. You take the sign or some other kind of thresholding. In other words, it's a whole lot like the expand and sparsify representation from the fly. Okay? It's a lot like what the fly is doing. And so this is one of the connections that we fleshed out. Okay? So it has many of the same characteristics. A lot of the same results apply. Okay. Yeah.
How large should D be, like relative to the original dimension?
So, right, how large should D be? So, so there are 2 things. So the first thing is like what's done in practice, okay? And the second is what does the theory dictate? So the theory tells you that, for example, if you want to store a certain number of elements, then D needs to be at least something. Say the log the number of elements you want to store. In practice, for some reason, 10,000 has been a magic number. So a lot of, like, D equals 10,000 is very common. Okay, so we're just trying to like map out exactly, like what it would be mathematically. Okay. So I wanted to actually bring up an open problem in this area, in case any of you are interested. It turns out that all of this, all of these applications and results only use element-wise addition, the bundling operator. They don't use the multiplication operation at all. So what I was saying is that in this model, you're allowed two different types of operations. So once you map everything to high dimension, you're allowed element-wise addition, which is called bundling. That's how we build sets, for example. We bundle them together. And you're also allowed element-wise multiplication. Okay? And the question is, what does the multiplication get you? Okay, so what, it's called the binding operator. So when we add stuff together, it's like building a flat data structure, like getting a set. The binding operation lets us build more complex structures. So for example, suppose I wanted to store a certain type of information. Suppose I wanted to associate my name with two attributes that I have. That the city I live in is San Diego, and my zodiac sign is Taurus. Suppose I wanted to associate that, okay? Then I would use the binding operator, and I would do it like this. I would first look at the encodings for each of these things, Sanjoy, city, San Diego, sign, Taurus, and so on. I would create a tuple in which I bind together city and San Diego, and bind together sign and Taurus. Then I would bundle these together and finally bind them to me. Okay, so this is how I would store it. Okay, so what is this binding operator doing? So in this case, all of these vectors are, these are all distinct items, and they're all vectors that you can think of as being approximately orthogonal. The hope is that this operator over here, this multiplication binding operator, is creating yet another vector, okay, that is also orthogonal to everything else, roughly, okay? And it's sort of creating it on the fly, because these are the basic elements that we had to start off with. And this binding is creating another vector that's orthogonal to everything else approximately, okay? And now we're bundling these together and associating it, and finally binding it to me, okay? And then you could have information about lots of people, and it doesn't have to be the same information. It can be different attributes. And you just add them all up. You just bundle them all together, and then you can retrieve stuff like, oh, what is Sanjoy's sign of the zodiac? Or list all people whose sign is Taurus, or that kind of thing, okay? So the question here is, so it's known that you can do this, but it's not known that, what are the limits of this? What exactly is it buying you? It seems that the bundling operator alone gets us something that's fairly close to linear sketching. And the question is, how much further does this go? And can we use it for simple types of reasoning, for example? Okay? So this is kind of an interesting question. And I don't think that this is something that people understand too well at all. Okay? So in this seems like a operation of hyperdimensional computing that really takes it beyond, sort of simple work in streaming, for example. Okay, so let me just wrap up. So what I was saying is that I'm really interested in these sort of, formalizing different types of neural machines. And before embarking on any sort of unifying formalism, I've been interested in looking at specific examples. And these are two of the examples I've been looking at. Okay, so I'd like to end by just thanking my wonderful collaborators.